Welcome all. So I'm Vishal Mishra. I'm the Vice Dean for Computing and AI at the School of Engineering. So this is the third lecture in our series on distinguished lectures in AI that we started in fall. It's part of the wider effort, led by School of Engineering of AI across Columbia. We are collaborating with other schools, other departments. We have a new website that you can go and check out where all of these events and other things are there. It's ai.columbia.edu. Easy to remember. And so there are lots of sort of AI related activities that are happening at Columbia. This year we actually taught a new class in the fall called AI in Context. It's still sort of ongoing, where the class was taught by a combination of faculty from the School of Engineering, from Arts and Sciences, philosophy, music, creative writing. And we announced it just 2 days before the semester started, and still we had about 80 undergrads sign up. It's quite popular, and we hope to continue to introduce that and other AI related classes. We are also sort of collaborating with other universities and other industries. We have this effort called Empire AI, where together with New York State and other universities, we are building this new data center devoted to training of these large models. And that's something our speaker, Danchi, is going to talk about. Uh, so before further, and I'll just ask Kathy to introduce Dancy. Kathy is the Henry and Gertrude Rothschild Professor of Computer Science. She is one of the legends in natural language processing, so there can be a better person to introduce Dancy than Kathy. Kathy, please.
Okay, thanks, Vishal. I also want to point out that today's lecture is co-sponsored with ARNI, which is our NSF AI Institute for Artificial and Natural Intelligence. So this is a collaboration at a sort of large scale between researchers in artificial intelligence and computational neuroscience, and we're looking for synergy between those two groups. Okay, it's my pleasure today to have Danchi Chen here with us. Danchi is one of the early stars within the field of language modeling. She burst onto the scene in 2018 with her PhD, which was one of the first that showed how deep learning could be used for a variety of tasks, for example, reading comprehension. Since then, she spent time, and I want to make sure that I have this correct, she spent time at Facebook AI Research before joining Princeton as an assistant professor. At Princeton, she co-leads the Natural Language Processing Group, and she is also the associate director of Princeton Language and Intelligence Initiative. This initiative was formed about a year ago, and it is a major part of Princeton's new AI Institute, which just came online a couple of months ago. Danchi currently focuses on training, adapting, and understanding large language models, and she's particularly interested in making this kind of work accessible within academia. She has won many prizes. She's been recognized by a Sloan Fellowship, an NSF Career Award, a Samsung AI Researcher of the Year Award, and Outstanding Paper Awards from ACL and EMLP. Danchi.
Can you hear me well? Okay. Yeah, thank you so much, Cassie, for the wonderful introduction. Yeah, today is my great honor to be here and speak with all of you. So this talk will be about training language models. And I would like to share some of my perspectives on how academic research can actually contribute to today's large language model landscape. So last weekend, while I was still enjoying the Thanksgiving holiday, I noticed many people were actually celebrating the second anniversary of ChatGPT. My first reaction was, wow, ChatGPT has been really only 2 years. As someone who has been working in NLP for 1 decade, so actually I published my first NLP paper in 2014, exactly 10 years ago. Especially focused on building the foundations of NLP systems. So ChatGPT was really a significant turning point for me for my research. So it actually really fundamentally changed the ways that how we think about NLP research. So it's incredible that how much has actually happened in the past 2 years. So clearly, even within OpenAI, this model have gone through several iterations or generations, becoming more and more powerful. So from ChatGPT to GPT-4 to GPT-4o, and the more recent O1 model. So beyond OpenAI, there are also other highly capable closed source models, such as Anthropic's Claude and Google's Gemini. At the same time, there are also models like Meta's Llama, Mistral, a Quant model from Alibaba, Gemma model from Google, and the Phi model from Microsoft. And they all have gone through several generations in the last 2 years. But there's a key distinction here between API models and also open weight models. So API models like ChatGPT, Claude, and Gemini basically only provide API access that only allow us to prompt these models and observe their outputs. But open weight models like Llama or Gemma, we can actually download this model, fine-tune this model, and hopefully we can actually better understand what these weights, the model weights of these models, and understand what they're actually doing. However, the lack of the transparency around their training process on data still makes it a significant obstacle for us to actually study the deeper scientific questions. There has been also a lot of growing interest in building open source models. This includes some really great initiatives, including AI Choose Almo, BigCode Star Coder, and the LL 330, and the Elusa AI Pacific models, and so on. These models have been, research institutions and also open source communities have been really committed to promoting fully open source models. There has been a lot of progress being made, but still we have to admit that the gap between the open source models and also the API models is still very large. So still, there has been a lot of really exciting developments going on in the past 2 years. But most of these developments in the model development are still taking place within the industry or large tech companies. So as an academic researcher, so in the last 2 years, I had to keep asking myself, so what kind of research should we actually focus on? And how can academic research even meaningfully contribute to the large language model ecosystem? Clearly, even if we don't need to train any models in academia, there are still a lot of things academics can contribute. And there are actually many successful examples. For example, one big important area is evaluation. So we can develop trend benchmarks and understand the progress of language models and what they can do and they cannot do. And this can be done for both API and open weight models. And another very important and popular direction is the agents. So even if we don't know anything about the inner workings of large language models, we can still build systems on top of these API models to solve very complex tasks that was actually not possible at all in the past. So for example, several of my colleagues at Princeton, they built a Sui agent, which is actually a large language model agent that can be used for software engineering. And there is also this very nice paper from Stanford, and they propose to use closed source models such as GPT-4 or Claude to generate novel research ideas, which is super cool stuff. And the third direction we can actually work on in academia is that we can also try to gain a deeper understanding and a mechanistic analysis of the large language model internals and their behaviors. And this can be done at least at the open weight model level. So my group has been also actively engaged in this area. So next week at NeurIPS, we will actually present this paper led by my PhD student, Aditya, who proposed an automatic approach to identify very sparse circuits in the large language models to actually try to understand how the computation is actually done inside transformers. So however, so these are the 3 areas that a lot of academic researchers have been working on. But this still feels actually really deeply unsatisfying to me. Is this all we can do in academia? Shall we always just take the models that have been shaped by industry without trying to understand how these models were actually developed? So in this talk, I want to actually ask the harder question that I've been actually thinking a lot. So how should we actually approach the training of language models in academia? First, you may want to ask, why should we even bother? Training models by ourselves in academia, in academic context, can actually help us answer a lot of scientific questions about literally every component of the training pipeline. So this really includes the training data, model architecture, training objectives, and the training recipes, such as optimizers, or what kind of data we actually want to use in different stages of training. I also deeply believe that only if we can actually engage with the language model training, we are actually able to come up with better and new solutions to make these models better, to make the training process of language models more efficient. And I also strongly advocate for the importance of developing all great open models that can actually benefit our research community. So the next question is, how should we do that? This is actually definitely a very difficult problem, a challenge. So I will just do a very simple calculation here. So let's say if we want to train a Llama 3 8 billion model from scratch. Here, I'm only talking about the 8 billion model, even not the 70 billion or 405 billion model. So the estimated training cost for one single run of training a Llama 3 8 billion is about 2 to 3 million. So which is already almost impossible for any academic labs. And there is another level of challenge here, that when industry can easily build a team of engineers for training these models, at the university, like most NLP groups, typically only have like 6 to 10 graduate students. And these students are not really engineers, and they also usually have very different research interests. So how can we actually bring students together to work together in training the language models? So we are in a bit lucky situation here at Princeton, as Cassie already introduced at the beginning. So at Princeton, exactly 1 year ago, we launched a new initiative called Princeton Language and Intelligence, or PLI. And the university has invested a big GPU cluster of 300 H100 to support fundamental research of large language models and AI models. So I know some other universities like Columbia also making similar investment and efforts as this year. So while this GPU cluster is no way comparable to the industry scale, at least it allows us to at least engage meaningfully in the model training. So I should at least mention that actually building such a cluster at the university is actually requires tremendous effort. And it actually took a lot of people really try to put together this cluster. And our cluster was finally optional, actually only this past summer. So now assume that we have some access to some GPUs. And I also happen to have a few students who are really interested in working on training large language models. So we still need to think very deeply about what we can do in academia. So what are the important research questions we can ask? And what are the opportunities in actually developing strong open models that can actually benefit the community? So to address these two questions, so I would like to give a very brief introduction to language model training to make sure everyone here is actually on the same page. So when we talk about language model training, there are usually two stages. The first stage is pre-training. It's actually a pretty quite fixed paradigm at this point. Basically, we just throw in massive unlabeled text, basically everything you can find from the internet. And then we train a model to predict the next word. So this is an equation I took from the GPT-1 paper in 2018. So basically nothing has changed at all since 2018. So basically the only factors we need to consider here are pre-training data, the model, like how many layers, how many parameters we need to put in this model, and also the context window, which is K in this equation. So the pre-training stage is known to be extremely expensive and it takes up most of the computational cost. And another big challenge, which is also a very fundamental question here, is the pre-training data is basically everything you can find from the internet. It's actually very difficult and challenging to study the pre-training data because these data are basically like the internet text. They are very highly unstructured, noisy, and massive and very large. And the second stage is post-training. So we can also refer to everything after pre-training as post-training. So although I would also claim that the boundary between the pre-training and post-training has become more and more blurred, because some models also start to put the supervised data in the later stages of the pre-training. So the goal of post-training here is to further fine-tune the model to follow instructions or align with human preferences, or improve some specific capabilities such as coding and reasoning. So roughly speaking, there are also two stages of the post-training. So we can call them instruction tuning and the preference learning. So in instruction tuning, so you basically just need to take data in this format of the prompt and the response pairs. And then you basically just need to perform supervised fine-tuning on this data to predict the response conditioned on the prompt. And in preference learning, and actually a more well-known term here is RLHF, reinforced learning from human feedback. So basically, we need to take the data in this format of the prompt and the winning response and losing response pairs. Then we can use either RL or offline preference optimization methods such as DPO to learn from this kind of preference data. So the post-training stage is actually usually much cheaper compared to pre-training, making it actually more feasible and also for academic research. And the paradigm of post-training is also not as fixed as the pre-training. So this still opens us up a lot of opportunities for exploring new training objectives and approaches. And also the data in post-training stage is also very different from the unlabeled data we use in pre-training. So this means that you cannot simply just extract this data from the internet, making the data collection also both crucial and also challenging. So for the rest of this talk, I would like to actually drop this talk based on these two stages, pre-training and post-training. So I would like to discuss some of the important research questions that I have been thinking about, and also share some of our latest work in both the pre-training and the post-training stages. So in pre-training, I would like to discuss two research areas here. So one is actually on small language models. These days, people call it SLMs, or small language models. And another area I want to talk about that I think is very important is how to understand the pre-training data. Okay, so the first research question I want to raise here is, how should we pre-train a small language model? So first, why do we care about it? The fact is people really like small language models. So here I refer to models, small language model as model with only 1, 2, 3 billion parameters. But today's in context, we can also consider basically all the models under 10 billion parameters as small language models. So compared to like models like with 70 billion or 400 billion parameters, these models are much easier to run and fine tune. And they have actually many use cases in on-device computing and adaptations. So next, I would like to introduce a paper we did, actually has been already 1 year old. So this paper is called Sheer Llama, and it was published at ICLR 2014. And this work was led by my PhD students, Meng Zhou and Tian Yu. So the key idea of Sheer Llama is actually very simple. So the idea here is we want to produce a small language model. So instead of training a small language model from scratch, let's try to prove a small language model from a larger existing pre-trained model. And then we do continue pre-training. I should note that here, the pruning stage is actually much cheaper compared to the continue pre-training stage, usually only taking less than 1% of the training compute. So here is one concrete example. So here we assume that we take a source model, which 1 year ago, which was Llama 2 7 billion model. And let's say our goal here is to produce a 1.3 billion model with a very specific target architecture. Let's say this model has 24 layers, 16 heads, and a hidden dimension of 2048. So we can prove this model architecture from the source model by basically removing the layers, the heads, and the intermediate dimensions to actually match the final architecture. So this is essentially a constraint optimization problem. So we can actually model all these pruning decisions, like pruning layers, the heads, and the intermediate dimensions as some masking variables. And we can also use some kind of, I'm not going into details, technical details here, but we can also use some Lagrangian constraints, multipliers and constraints to actually control the exact final architecture we want to prune. So this is actually also built on our prior work by Mengzhou in ACO 2022 work. So if you're interested, feel free to check out. Okay, so this is about how we do pruning. So we prune a smaller model from a large model with an exact model architecture. So the next question is that we want to do continual pre-training. We want to continue pre-train this smaller model. So the next key question here is what data we should use to pre-train. So this is actually very important and also broader research question in the context of pre-training. So how should we actually decide the data mixture of different domains? And this turns out to be actually a crucial deciding factor in determining the model performance. So I'll give you one example here. So this is off-the-shelf pre-training data. It has been actually 1.5 years already, called Red Pajama, released by Together AI. So the pre-training data consists of the 7 domains: Common Crawl, C4, GitHub, Books, Archive, Wikipedia, and Stack Exchange. And each has very different domain ratios. So we can basically, like, if we want to do the continued training, we can basically just take this off-the-shelf pre-training data and do the continued training of this data. So if we just do the uniform sampling from this data, we actually find that the loss difference compared to, let's say, training this smaller model from scratch is actually highly imbalanced across very many different domains. So here we found that the loss difference on C4 is actually much larger. And for example, for some domains like GitHub, the loss difference is actually significantly lower. So in this work, we actually propose a very simple solution called dynamic batch loading. So which essentially uses the source model, which is actually the Llama 2 7 billion model, to provide a reference loss, which uses that reference loss to actually guide the domain mixture for different domains. And we can essentially just try to adjust the domain mixture and then continue pre-training the small model on this domain mixture. So I'm not going to explain the equation here, but the idea here is basically try to load more data from the domains that the loss reduction is actually slower. So we try to use more data from the domains that there's still much larger gap, and try to use less data from the domains that actually the loss is actually pretty good. So it turns out how to choose this domain mixture is actually very important. And after we use this dynamic batch loading, we end up using actually more C4 data and the Books data, and also less Common Crawl data. And this also leads to significantly better downstream task performance. And for example, if you look at this figure, if you compare the red, which is our dynamic batch loading, and to the basic blue curve is the basic uniform sampling, it actually leads to much better performance in terms of downstream tasks. So this idea of shared llama has proven to be quite successful. So we actually demonstrate that structured pruning is a far more cost-effective approach for building small language models. So compared to, let's say, if we train a model from the scratch. As you can see from this table, at that time, like maybe 1 year ago, if you look at all the small language model out there, they're all kind of pre-trained from scratch. But our model was started from the Llama 2 7 billion model. And then we actually end up using only 3% of the training compute compared to the other models, which actually achieved comparable or even better downstream task performance, as you can actually see from the figure on the left. And also, after we wrote this paper, we basically open sourced our the artifacts. So we released 2 models called Shared Llama 1.3 billion model and 2.7 billion model to the community. And actually, to our surprise, this is actually really more like academic artifacts. These models have actually become very popular. Even today, we have actually much stronger small models. These models still have like 70,000 downloads per month on Hugging Face. And the people actually find these models quite useful in a lot of different use cases. For example, you can use smaller models as draft models for decoding, or you can use this smaller model for video captioning and many other tasks. And also more recently, we actually also observed this trend in industry, which actually follows this idea of producing small language model from larger models. This actually includes the Meta's Llama 3.2 models and also NVIDIA's the miniature models. So here is the one figure of the Llama 3.2, basically which includes two models, 1 billion models and 3 billion size models. So if you just zoom in and look at the area highlighted in this red box, you will basically see that they actually start from the 8 billion and 70 billion Llama 3 models and to provide some pruning-based initialization for their 1 billion and 3 billion models. So this is actually really similar to what we did in SheerLlama. Okay, so next, I would like to shift my focus to the other part of the pre-training and discuss another aspect of pre-training, which is actually how to select high-quality pre-training data. So we all know that high-quality pre-training data is really the key to the success of language models, at least at the pre-training stage. But how should we even define the quality? And how can we actually measure the qualities in the in the pre-training data? And how can we even sample data based on these quality measurements? So to address these questions, next I would like to introduce another paper we did this year called Curating. And this is a paper we published at ICML 2024. And this work was led by my PhD student, Alex Vettig. So when we started working on this data selection or pre-training data project Curating, we were actually a bit surprised to find that the existing work on pre-training data selection were still really simple and heuristic based. So most approaches in selecting pre-training data, they either rely on like the rule-based filters, such as the famous CFOR or Gopher rules. Or some other works, they basically try to select texts that can match the distribution of some high-quality text domains, such as Wikipedia. So on the right, you can see some of the CFOR rules that have been actually widely used in industry. For example, people just try to keep the documents or keep the sentences that end up with some punctuation marks, or they try to just discard the documents that are actually fewer than 5 sentences. So in this work, our work Curating, so our aim was to understand what qualities of text actually matter in pre-training, and whether we can actually select pre-training data based on the human intuitions of our data quality. So even if we can actually try to quantify all these kind of human intuition, the abstract qualities of the pre-training data, so the next question is how should we actually translate them into some kind of quality ratings at a larger scale? So here's our idea, actually very simple. So we basically take any pair of text from the pre-training corpus, and then we use a language model. And in this case, we use a GPT 3.5 Turbo model, and to compare the different pairs of text across the different qualities. So for example, here we ask, which text has a better writing style? And which text has more contains more facts and trivial, and which text has more educational value, and which text actually requires greater expertise. So this just are the 4 abstract qualities that we define in this work, but the framework can be easily extended and scalable to other qualities of interest. So we did a lot of pilot experiments. We actually ended up finding that the large language models actually perform really well in discerning this kind of abstract qualities between the text pairs. And especially during this kind of pairwise judgments, models can be actually very confident to tell that which model or which text is actually better in at least one of these dimensions. So let me just give you like an illustrative example of this process. Here we take a pair of texts. So text A is like probably a document from a news article. Text B is basically a code snippet. And then we basically try to just ask the GPT-3 language model to actually tell like which text has more polish and beautiful writing style. This is basically the prompt we wrote in terms of the writing style. And the model tells us, okay, the text A has better writing style. And then we ask the next question, which text contains more facts and trivial? And we saw like pretty well defined the prompt here. And the model tells us, okay, text A has more facts. Similarly, we did this for educational value and also required expertise. And the model can basically tell us the text B has actually contains more education value than required expertise. So after we collect all these kind of pairwise judgments, essentially we just need to figure out how to convert this kind of pairwise judgments into this kind of quality ratings along all these different dimensions. So in our experiments, we essentially collect 250,000 text pairs from the 500,000 unique documents, and we collect the kind of language model pairwise judgments. And then we fine tune actually pretty small language model, actually based on our 1.3 billion sheer llama model. Is actually essentially a Bradley Terry ranking objective that can actually convert this kind of pairwise judgments into the quality ratings. So essentially we collect all these kind of pairwise judgments, and then we train a small model to actually finally assign a quality rating to every single document. Then we can actually use this small model, 1.3 billion model, to actually assign the ratings to basically every single document in our pre-training corpus. So after we produce all these quality ratings of the pre-training data, we can actually use these quality ratings to do a lot of great things. For example, we can use the quality ratings to actually understand the data distribution in different domains. So here we can see that basically we made a lot of nice plots like this in the paper. And you can see that the books domain actually has on average the best writing style. And the Wikipedia has actually more facts. And the archive actually requires the most expertise. This is just average. But even within each domain, there has been quite a variety along every single dimension. So now we have the quality ratings. So the next question is, how can we actually sample the data with respect to these quality ratings? So there's a very important observation here is you actually need to balance the quality ratings and also the diversity. So here we just use this very simple equation to actually sample the documents to decide the probability of one document being chosen, being sampled. And we use this temperature term here, the tau here, to actually try to control the balance between the quality and the diversity. So when tau is actually 0, that basically means that this falls back to we just need to select the top K, the most highest quality documents. If tau is actually infinity, essentially this also falls back to the uniform sampling. So in all our experiments, we first annotated the slim pajama, which is a filter version of the red pajama, using our curator model to basically assign the quality ratings. And then we select 30 billion tokens out of the 260 billion pre-training corpus with all the domain proportions fixed. Then we train the 1.3 billion, a lot of 1.3 billion model from the scratch. So here are the results. Actually, the final results are actually very interesting. We found that actually a lot of previous baselines basically didn't work. And then if we just select the documents with the highest quality ratings, and we found that actually they also don't perform really well. But if we can actually control the good balance between the quality and the diversity, when we use the tau of the value of 2.0, we actually can improve performance in both the perplexity and also downstream task performance. This also can give us actually a very fine-grained understanding in terms of what quality actually matters. For example, we found the educational value helps a lot on the reading comprehension task. But if we focus too much on the writing style, this actually hurts the performance on the knowledge-intensive task. But in general, the quality matters. And we need to really figure out how to select the high-quality data from the pre-training to actually make our models better or to make the pre-training more efficient. Finally, I just want to say here that I feel that we have only scratched the surface of the understanding of the pre-training data. The more recently, there has been actually a clear trend of using these kind of model-based signals for pre-training data selection. So similar to what we did in curating. So this is one example. This is called FineWeb EDU, released by Hugging Face this past summer. So they basically focus on selecting high pre-training text data with high educational value. So the idea here is also very simple. They basically just prompt the Llama 3 70 billion instruct model and try to let the model, this is actually the prompt they used, to let the model to tell like which documents contain like what level of the educational value. And they actually produced pre-training corpus with this quality filter, they call it FineWeb EDU. And they actually demonstrated very significantly stronger results compared to other pre-training cohorts, as you can see on the right. Okay, so let me summarize this part. So I think small language models are actually very exciting venue for academic research, as we showed in the sheer lamp. And actually a really bigger and also unresolved question in the pre-training space is that we actually need to develop systematic and principled understanding of the pre-training data, which actually can potentially shape the future of the pre-training. So this really includes understanding both the quality signals and the quality filters, and also how to compose the data, and how to decide the optimal domain mixtures. And an even more general question is, what should be actually a domain? Right now, we just use very coarse-grained domains, for example, Common Crawl. That's basically really the data that you crawled from the internet. This is clearly too coarse. It's not really good enough for us to really figure out the domain mixtures. Finally, I also want to point out one potential caveat here of the academic research. For a lot of things we have been doing, including the curating projects. So with the computer we currently have, we can basically do our best. We can still only afford training 1 billion size models on, let's say, 30 billion to 110 billion models. I know a lot of the model architecture research right now is basically also focused at this scale. This really still opens up a lot of questions and also opportunities about whether these findings can actually really generalize to or scale up to larger models, and what the scaling laws actually look like if we can scale up. Okay, so this is my first part on pre-training. So let me next move on to the second stage of the post-training. So I already discussed this at the beginning. So for post-training, usually we consider two stages: the instruction tuning and the preference learning. Instruction tuning essentially just learns from this kind of prompt response pairs and try to use the next token prediction to predict the response condition of the prompt. And the preference, so basically the training objective is very simple and also very straightforward. But for preference learning, on the other hand, it actually involves learning from the prompt and also pair of the winning and losing responses. So the training objective for the preference learning process is still an active research area today, and which I will discuss shortly. So let me first quickly discuss the instruction tuning stage. So in the recent years, there has been actually an explosion of the instruction tuning data sets in this form, the very simple form of the prompt response pairs. So I believe now we have at least hundreds of millions of data points available of this instruction tuning data for supervised fine tuning. Some of these data sets, for example, natural instructions, are repurposed from the existing NLP data set. And some other data sets, such as Dolly or Open Assistant, they are purely human written. And there are also some other data sets, for example, like Shared GPT, the responses actually distilled from ChatGPT. And there are also some data sets, for example, Stanford's Alpaca data set. They basically try to even distill the instructions from the ChatGPT. So both the prompt and the responses can be actually either human written or model generated. So let me give you an idea of what the state of the instruction tuning looks like. So this is from the Tulu V2 paper from Allen Institute, AI2. So they basically did a lot of trial error. And they finally curate this subset of instruction tuning data they call Tulu V2 mix. So it's from many different open source data sets. So this ensures that if you look at this very long list of the instruction tuning data sets, so they actually really differ in both in the source and the distribution of the data and also the size. So it's actually very difficult to actually determine whether such manual efforts actually are optimal or not. But as you can see from the table on the right, so they basically try to propose Tulu V1 mix and the Tulu V2 mix. But clearly, the data mixture matters a lot. And the V2 mix outperformed the V1 mix by a very large margin. So the bigger research question here is, how should we actually, given there are so many different instruction tuning data sets, how should we decide what instruction tuning data set to use, and how we should select examples from each instruction tuning data set to achieve better performance? Just for the sake of time, I will be very brief about this part, but I want to mention one paper we did called LESS. So this is a project led by Mengzhou and Sadika at Princeton and presented at ICML early this year. So our goal here is to, instead of repeating all these manual efforts, we try to propose better ways to automatically select training data. So our key idea here is to use the inference estimates to predict how much impact each instruction tuning data point can actually have on the validation loss. And then we try to choose the training data, the instruction tuning data that can maximize the reduction or the validation loss. So we also made this work with the Adnor optimizer. So this essentially algorithm is essentially actually model aware and also optimizer aware. We also did a lot of the efficient approximations in our paper because it's actually essentially a very difficult task if you want to use this kind of gradient features to actually do the data selection. So we actually did something like the random projection of the gradient features onto a low dimensional space. So we can actually enable us to actually do the data selection very efficiently through the similarity search. So if you're interested, I encourage you to check out this paper. But the results are actually very surprising. So we found that in at least all the experiments we tested on, we can actually often only select 5% of the instruction tuning data sets that can often outperform using all the instruction tuning data sets combined. And the gradient features, we actually we learned from this for this data selection process can be actually even transferred from a smaller model to a larger model, or even transferred between the different model families. For example, here we have one variant called LEST. Essentially, we try to use the Llama 70 billion model to construct the gradient features. And then we fine-tune and then select the data points. And then we fine-tune the Mistral 7 billion model on this like 5% of the selected data according to Llama 7 billion, which still works very well. Okay, so the last part of this talk I want to talk about is actually the preference learning or learning from preferences. So you may, I assume that many people here are already familiar with the idea. But first, I want to ask a question: why do we even want to models to learn from the preference data in this format of the prompt and the winning response and the losing response? There has been actually a lot of great justification to that. But intuitively, you can think about this. So in instruction tuning, essentially, you just learn from only the correct output, the X and the YW. But preference learning can actually learn the difference between the correct and also the incorrect output. This is actually very important for safety tuning or factuality, and also many other dimensions of the model capabilities. So here's one example. So the prompt here is, why aren't birds real? So the response one is, birds are not real because they are not made of flesh and blah, blah, blah. And the response two is, I'm sorry, I don't really understand the question. Birds are very real animals. They have been observed and studied extensively throughout the history. Okay, so both outputs are relevant, fluent, but clearly, if we ask humans to select which one should be the correct one, clearly only the second output, the response two, should be actually preferred, and over the first response, as according to human values. Okay, so this is basically the idea of learning from preferences. There are actually different ways to learn from the preference data. So the canonical solution here is to use RLHF, reinforced learning from human feedback. So which basically means that you can learn a reward model first from this pairwise preference data. And then you can use reinforced learning to optimize the policy model according to this reward model. And there is another alternative way to do this. It's also called offline preference optimization. So the idea here is basically, instead of learning a reward model from the preference data first, you can actually directly optimize the language model from the preference data. And the most notable example here is called DPO, direct preference optimization, proposed by Stanford researchers last year. So I'm not going to really how the details of how the DPO was derived, but DPO essentially starts from objectives that are similar to RLHF, and they try to derive, reparameterize the reward function using a closed form of the optimal policy. And then finally, they derive this training objective that are used directly to learn from the pairwise preference data. What I want to emphasize here is DPO is actually really a huge thing for academic research, right? This is really like a research paper from a university, but this has really deeply influenced how a lot of industry practices. For example, the Llama 3, the post-training stage, heavily built on the DPO, and is really a big component of Llama 3. Okay, so finally, the remaining research questions here is, can we do actually better? So this actually includes designing both better training objectives for preference learning, and also better developing better training pipelines for improving the model performance. So next, I'm going to introduce basically the last piece of work we did this year called SimPO, which essentially is a new and simpler training objective for preference learning. And this work was led by Yu, who is now assistant professor at the University of Virginia, and my student Meng Zhou. So essentially, SimPO is actually similar to DPO, is another training objective for offline preference optimization. But besides this new training objective, what actually surprised me actually most in this project is we are actually able to develop a very strong model just in the academic context based on the Google's Gemma 2 model. And it turns out this model we call Gemma 2 9B instruction tuning simple model. This model turns out to be actually the strongest model under 10 billion size parameters on all the important chat leaderboards, including Chatbot Arena, Wildbench, Arena Heart, and the Alpaca Eval 2. So this actually really surprised me, and I will show you how we got that. Okay, so what is simple? So it's a simpler training objective for preference learning. So I don't want to talk too much here, but I want to put a comparison of the DPO and the simple objective here. So if you look at the equations of the DPO objective and the simple objective, the main difference here is, so first we get rid of the reward function. Oh, sorry, we change the reward function. We get rid of the reference model from the reward model, a reward function. And then that's basically the PyRef in the first equation, and usually implemented as a supervised fine-tuning model. And then we simply just use a length normalized version of the log likelihood, the basic condition of the prompt, try to predict every single token in the response as a reward function. Finally, we'll also introduce a target margin term called in the gamma in this equation, in this Bradley-Terry ranking objective. So the key idea here is we believe that the reward function of the simple, without this reference model, is actually more aligned with how the language model is actually used during the generation. So there is actually a concurrent work from NYU and Princeton that actually show that DPO actually really flips ranking between the winning response and losing response. So we actually observed a very similar thing. As you can see from the figure in the right bottom here, is that so one axis here is to compare the probabilities of the winning response versus the losing response. And another axis is to compare the reward of the winning response and the losing response for both DPO and the simple. Well, no, we found that actually that in the DPO, the probabilities and the reward actually not well aligned. So in the paper, we actually did a lot of analysis trying to compare simple and the DPO. So if you're interested, feel free to check out. So let me show you some results. So we have done extensive experiments in this paper, including using both the Mistral and Llama 3 model. And using both the base model, that means the model only pre-trained. We did the supervised fine-tuning by ourselves. And also the instruction-tuned model, which means that this model already post-trained. So in all these scenarios, we find that simple actually outperforms DPO consistently. And in some cases, the gains are actually pretty large. Finally, I want to tell you this thing, this simple recipe we did, that we actually were able to produce this open source model called the Gemma 2 9B instruction tuned simple model. So this is a very simple recipe. So the basic idea is that we start from the Gemma 2 9B instruction tuned model. So this means that this model is already post-trained, but we actually know very little details about what is actually going into the pre-training and also the IIHF stage. And then we just simply take only 50,000 prompts from an open source data set called Ultra Feedback. So which is basically a collection of a lot of different instruction and prompts from the different sources. And we use this Gemma 2.9b model to generate 5 responses. And then we use another external reward model called ARMOR-IM. This is also another academic research result from a research paper from UIC. Is a external reward model. And we use this ARMOR-IM reward model, the best response and the worst response among the 5 responses that we generate from the Gemma 2.9b model. And as a winning response, YW, and the losing response, YL. Finally, we just train the simple on this on-policy data. It's called on-policy data because all the responses actually generated by the current model. Then we got this final model, Gemma 2.9b, instruction to the simple model. What I want to emphasize at the end here is this process is actually really lightweight. It really only requires less than 3 hours on the 8H100 GPUs, which is actually very doable in academic context. Even if you don't have H100, you can still use like a weaker GPUs, but it's just totally doable in academia. But what really surprised us is just by applying such a simple recipe, we actually can get a much stronger chat model. For example, if you look at the rankings on the chatbot arena, which is really the canonical leaderboard that a lot of industry companies are actually really competing against, right? And we actually able to move the ranking on the chatbot arena, the ELO rating, or like rated by the real users from basically the rank of 50 to 35. This is actually really a big boost. So this model essentially even surpassed a lot some other chat models, for example, Llama 3 70 billion model, instruction model, E-large model, and some version of the cloud models. So this actually really, we are really happy with this result. Okay, so let me conclude this part. So I actually believe the post-training stage still has many research opportunities in making a real impact in terms of both the training data and the training objectives. So compared to the pre-training that we just need to throw in a lot of the unlabeled text from the internet, we are now actually back to this paradigm of the supervised data, supervised fine-tuning. There are actually a lot of different data questions that we can actually ask here. So whether the data is human annotated or the model is the data is model generated. So whether the data is actually on-policy data or off-policy data, that means the data actually generated by the current model, or the data is actually already static data that already produced by other models. And another really important question is, how should we actually even collect a truly diverse set of prompts to ensure that our models can actually generalize to many real-world use cases? And for the learning side, algorithm side, he was still exploring a lot of these different algorithms, including RHA, offline PO methods like DPO or simple, or we can actually do a combination of both. Finally, I also want to point out a caveat here in terms of academic research in this space. Today, a lot of research we're actually doing in this space, including the simple work I just showed you, still built on the open weight models such as Llama 3 and Gemma 2. That means that it's actually still not yet a fully open source training pipeline, because we don't really know what pre-training and the other chips have already gone into the kind of open weight models. I'll just give you one example. When we developed the simple in our research project, we actually observed very different trends of the catastrophic forgetting when you apply simple to Llama 3 versus Gemma 2. But we cannot really know why, because we don't really know like what data is actually going into the Llama 3 and Gemma 2. So this is still not satisfying, but it's actually one of the reality we are facing right now. Okay, so I'm almost done. So finally, just let me wrap up this talk. So in this talk, I was hoping to share you some of my takes on how we should actually approach the training of language models in academia, including both the pre-training and the post-training stages. So I talk about some of these research areas like small language models, understanding pre-training data, and do better in both instruction tuning and preference learning. But still, all these research questions I discussed today still fall in these kind of most common practices of today, what industry people are doing in terms of training language models. So there's still actually many other orthogonal directions that we can actually explore and study. So one direction that my group has also heavily invested is actually long context and the retrieval augmented language models that I didn't get a chance to talk about today. But recently, we actually also released this series long context model called ProLong, which can support up to 512,000 context lengths. Again, this is actually still on our academic budget. So we actually end up showing that we are able to use only 5% of long context training budget compared to Llama 3.1, which can actually match or even outperform the Llama 3.1 performance on the long context task. So this really means that we can still play smarter by actually using less compute, right? And the other directions include training language models to solve really complex reasoning tasks. With actually since the OVA developed, I think there are a lot of people really thinking about in this area and trying to really figure out how to train language model to solve some really, really hard problems. Finally, I also think that academia should also invest in alternative model architectures. So the most notable example here is actually the Mamba, which is actually developed by my colleague Trida at Princeton. So which is a really like academic product, right? So that really shows that you can still develop like smaller-ish models in academia that can actually really make a big impact in industry and also the large language model ecosystem. So after engaging with a language model training for 2 years, almost 2 years, now I have gained more and more confidence that we can actually do a lot of things in the academic context. There's still a lot of really interesting research questions we should ask. So I think I will just end this talk with this line that I think we actually need more creative ideas than compute, but we do need some compute to do things. Okay, thank you so much for listening, and I'm very happy to take questions.
Hello, thank you so much for this amazing presentation. It was very neat and very easy to follow. So I am an undergraduate second-year student. So unfortunately for me, I wasn't familiar with a lot of these equations and whatnot. But I would love to get involved in this field. Do you have any advice for possibly on me and other undergraduate people in this audience, how to branch off into this kind of research, and if there's any specific field of research that you might recommend, like SLMs?
Yeah, definitely. This is a very good question. I would say these days it's actually very easy to be engaged with open source community. There are just a lot of really amazing learning materials on the internet. But there are so many research papers, I have to admit, that you have to really follow and really study all these really good research papers. And also try to join some kind of open source efforts. I would say that could be a good starting point. But also on the other hand, I would also admit that it's actually I feel pretty frustrated to read some papers from, let's say, some big tech companies, because they release some technical reports, but they don't have enough details. But I would say just try to focus on reading really good research papers and really come out the good ideas from these papers.
Thank you. I was wondering about the SimPio paper. What is the intuition behind removing or why the performance improves over DPO when you remove the reference model?
Yeah. I'll just give a quick answer. So yeah, it's actually very hard to go back, so I'll just answer it directly. So basically our intuition is during the decoding, you actually essentially just need to bring several sampling from the policy model, the language model. You actually don't need to use a reference model during inference. But during training, you're essentially using this Bradley-Terry ranking objective that try to maximize the difference between the reward of the winning response and the reward of the losing response. So we believe that there is such a gap, discrepancy between the pre-training and also the inference. And so the DPO paper, they derived this from the RLH objective in terms of its optimal policy, but in practice, it's actually very hard to actually achieve the optimal policy. So basically, my quick answer is we believe there is a clearly discrepancy between what DPO was trained and what is actually used in inference. And that's why this is a figure I showed in the presentation, that we find also some other papers show that DPO actually really flips the ranking between the winning and losing responses.
Okay, thank you very much for the talk. So I think the majority of the models you mentioned here are based on the transformer architectures. And then except this Mamba will be just a state space model. So I just referred to Jan LeCun's lecture, and he just mentioned the autoregressive language models are doomed because of the fundamental flaws of the state tracking and also hallucination. So we just build. I'm adjunct faculty in Columbia, and also I'm engaged with the company. We built large language models for different customers and different purposes. And one thing I realized is complain about the hallucination. It's a lot. And then there are different expectations that hallucination will never been effectively addressed. And I think in academia and also in industry, we need to just move out of transformers. Have you thought about it? And what is your idea about specifically state tracking and hallucination? Because fundamentally transformers are designed like a simple monoid problem, like a TC0, like a time complexity. And we cannot do, this is the nature of it. And we cannot, even just fine tuning, whatever you do, just selecting nice selection of the data. So industrial experience, we were not able to do anything about it.
That's definitely a great question. I don't want to claim I'm an expert in model architecture, but we do spend some time thinking about this. First, we definitely have seen a lot of the really promising results in state-space models. And a lot of people actually believe that maybe the future should be actually some kind of form of the hybrid model, that we actually need to bring this state back. But still, this model still face a lot of challenges of scaling up. So right now we see also a lot of recent evidence showing that you can actually alternative the two types of computing units, like the full attention model layers and also the state space models. They can actually achieve the best of both worlds. This is something we want to start it, but I don't have really perfect answer to that.
Thank you so much for the great talk. I was interested in two things. So first, oftentimes we right now use this paradigm of the teacher-student models, right? Where we use where we say, okay, maybe some data is higher quality, and we'll use GPT 3.5 or whatever model as this oracle. But at the same time, we're claiming okay, these models were trained on low quality data. How can you square this this conflict, right? Where we're simultaneously claiming, okay, this is our gold oracle, and then the gold oracle is fundamentally flawed.
Understand. When we work on the curating project, so one major question we got is this actually a form of distilling from ChatGPT, right? But essentially, we've actually viewed this as eventually we hope to have a way to scale up, for example, using human annotations. But ChatGPT at least is actually provides a good proxy. It just really only provides this kind of pairwise judgments to compare the text. It's definitely not optimal, but I see it's actually a quick solution for us to actually have a good understanding of the data. Whether we should view the ChatGPT as a kind of upper bound for this, honestly, I don't know. Right now, there have been a lot starting in weak to strong generalizations kind of stuff. Yeah. Hopefully, we can actually figure out a better way to bootstrap this process and to use a weaker model to actually annotate data and to get more and more high quality data.
And if I can also ask the second question. So you have mentioned that you were able to distill these smaller models that perform reasonably well from a larger model. I was also wondering whether now that we know that some of this data, pre-training data is low quality, whether we can also distill a model that might even perform better than the larger model, or whether we can have a pre-training strategy then that essentially takes this pre-trained model on low quality data and improves the performance further by given that we know which data from the pre-training data set might be higher quality and which might be lower quality, so that we So we avoid this paradigm of like retraining the model again and again and again from random weights.
Honestly, I'm not sure if I follow the question. There are two things here, the smaller versus larger model and the high quality data versus low quality data. Would you just-
Yeah, so sorry, let me just, simple question. Can we distill a smaller model that can perform better than the larger model? Or do you think that's fundamentally impossible?
I don't view things this way. Even for the Share Llama, we did is we only use a larger model to provide initialization. We have to do a continued pre-training. But just because we did it using pruning as to build an initialization, it saves a lot of compute at the first stage that is compared to pre-training from scratch. And after you finish the pre-training, which only takes 1% of the training tokens, and we can actually continue pre-training, use a lot of the compute to continue doing this and making the model better. So there is actually one curve I was not able to show in this presentation is that we actually use the pruned initialization, this Share Llama model compared to another existing small model that trained from scratch. And then we continue training, we actually see better curves if we start from the pruned initialization model.
Thank you so much.
Okay, hi. Thank you for the talk today. And I'm Peter. I'm affiliated to Mass Department Columbia, and we are also working on parameters optimization right now. So I got like a general question. So basically, the recent works we got two directions. One is from the data set, like your new paper, unintentional misalignment. We go back to the embeddings and do the deletion. One is like from the model set, like those different variants of DPO, like simple, IPO, etc. So I'm curious about how you think about this question. Should actually the model drive the data? Like we refine our model based on like the refined data, or actually it's inverse. We got a model first, and we then refine our data based on the model quality.
That's a very good question. Let me think about this. Right now, I view we are still at a stage that there just has been explosion of the data using either both in both the pre-training data and instruction tuning data. There isn't any quality control. And right now we are essentially trying to use this kind of model-based signals. But actually how to get the model-based signals correct is also very hard to actually try to get some features or get some information from the data to do something. We are still far from like hitting really the upper bound or learn from the mistake, suffer from the mistakes of this model adaptation. That's my current understanding.
Great, thank you. Like I got another short question, but like, okay.
I'm happy to chat more offline. Let's thank our speakers. Thanks so much.